Welcome back everyone for more statistics. Just as a reminder, this video is meant to be a Chapter 3 review for my class, Chapter 3 in statistics that is. So if you are not here for linear regression, then look somewhere else. Okay, let's move on to the questions. Number 9. Suppose that the following information was collected, where x is the diameter of a tree and y is the height of a tree. Okay, so we have a bunch of diameters and a bunch of heights. The least squares regression line for the equation is y equals negative 3.6 plus 3.1x. What is your estimate of the average height of all trees having a trunk diameter of 0.7 questions? And I know some people might be thrown off by an estimate of the average height. But that's just really what is a prediction from our least squares regression line. Okay? Our least squares regression line tells us what we think on average our prediction, our response variable is. So let's write down our LSRL in context first. Now that we have a nice looking LSRL, let's substitute. We want to know for a trunk diameter of 7 inches. And finally, let's calculate the predicted height. So our predicted height gives us 22.3. So our estimated average height of all trees having a 7-inch trunk diameter is 22.3 feet. Moving on to 10, we have a least squares regression line predicts that a tree, the height of a tree in its first 10 weeks of a nursery to be y hat equals 3.2 plus 1.8x, where y hat is the predicted height, and x is a number of weeks outside the nursery. So now we're looking at multiple part questions. So first, we're going to interpret the meanings of y-intercept and slope. So go to the sentence frames, because you're going to need the sentence frames. While we're here, let's copy the interpretations for slope and y-intercept. Now our response variable is height, so we're going to change all our response variables to be height in inches. Next, our explanatory variable is number of weeks outside the nursery, so we'll make that swap. Next, we're going to substitute the value of the y-intercept. So the y-intercept is 3.2. We see that here. And the slope is not 22.3. The slope is 1.8, positive 1.8. Finally, we're going to adjust for readability. So the value of height in inches when the number of weeks outside the nursery is 0 is 3.2. I have the wrong unit here. This is not 3.2 weeks. The heights are in inches. So reading through this first interpretation, I don't think I need to know the word value of the here. That's not really necessary. So the height in inches when the number of weeks outside the nursery is 0 is 3.2 inches. Inches sounds like it's redundant because it's both here and here. So let's get rid of this one in inches up here. That's not really necessary. Okay, so the height when the number of weeks outside the nursery is 0 is 3.2 inches. We have just adjusted that for readability, so we're good there. I think this highlight went here. And let's adjust the second one for readability. For every increase of 1 unit of the number of weeks, so for every increase of 1 week outside the nursery, I think that's a better way to say this, the height in inches, just like before, we probably don't need this in inches part. So the height, oh, we forgot the increases and decreases. And I said earlier that the slope is positive, so that means that the height is going to increase. So the height increases by about 1.8 inches. And I think that's well adjusted for variability. Let's read that one more time just to make sure. For every increase of 1 week, I think 1 week, outside the nursery, the height increases by about 1.8 inches. So good. Make sure you take those and you adjust them for readability. You don't want to sound too robotic on these. Part B. Estimate the height of a tree that's been out of the nursery for 6 weeks. Well, what is the regression line? So the predicted height is 3.2 plus 1.8 multiplied by the weeks. How many weeks are we saying for part B? We're saying 6 weeks, so substitute 6. And then now just do a little bit of mathematics. Great. Look how nice this is if you keep to the LSRL form that I've been trying to get you to stick to. If you keep this form, reading through that answer, predicted height equals 14 inches, as soon as you put inches there, then that's a complete sentence. There is context here. There is nothing else you have to write. Writing up a summary statement here is probably not going to add anything to the clarity to this, although you certainly could if you wanted to. Finally, for C, we have the actual height of a tree that's been out of the nursery for 6 weeks was found to be 12.5. Calculate the residual. Remember that for residual, the equation is RAP. Residual is actual minus predicted. Substitute numbers. Do some mathematics, and then you get the residual is about negative 1.5 inches. Well, that was a multi-part question. Let's take a look at 11. Maybe take a quick breather. Jeez. 11. An LSRL between train departure time after 5 p.m. and travel time found an R-squared of 0.66. If the relationship has negative correlation, okay, so negative correlation means that the slope of the regression line is negative. So what is the value of R? Well, R is just going to be the negative of the square root of 0.66. Now that's negative because of the negative correlation. And that gives me negative 0.8124. Explain the value of R squared in context. Well, we're just going to get that sentence frame again, aren't we? Let's substitute the things we know. What was our value for R squared? 0.66. So about 66% of the variation in, let's see, the response variable is travel time, is accounted for by a LSRL with, well, our explanatory variable is departure time after 5 p.m. So not a whole lot to do here. We've already talked about, hopefully you have a good idea about what these sentence frames mean based on what we did in class. So this should make sense. About 66% of the variation in travel time is accounted for by a least squares regression line with a departure time after 5 p.m. So I like to think of it as 66. The least squares regression line is about 66% better than just predicting based on the average travel time. Lastly, part C, what quantity is minimized by the least squares regression line? Well, it says it right in the definition, least squares regression. So the quantity that's minimized is the squares. Okay, so the least squares regression line is going to minimize the sum of squared residuals. Wow. I don't know about you, but I'm getting a little bit of tired right now. A little bit of tired. But we're going to push on to letter C. We have a paper, The Feeding of Predaceous Fishes on Outmigrating Juvenile Salmonids in the John Day Reservoir, Columbia River. Well, some things you should know is that a juvenile salmonid is, well, that's just a baby salmon. So this paper is going to plot the maximum size of a salmonid consumed by a squawfish. I'm just going to say squawfish instead of northern squawfish. So the maximum size of a baby salmon that was eaten by a squawfish and the length of the squawfish, both in millimeters. So the squawfish is eating the baby salmon, and you would imagine that depending on the size of the squawfish, the biggest salmon that I can eat would be based on the size of the squawfish. In other words, the bigger the squawfish, the bigger a salmon, baby salmon it can eat. So the regression line yields the following computer output. Here's our computer output. And I'm going to highlight some of the parts for you. First of all, we've got A. You can tell which one's A because it's next to the word constant. So here's A. Whatever's left over under the coefficient, that is B. Other important numbers you need to know are S. S is, of course, the standard deviation of the residuals. This one right over here is R squared, even though it says RSQ. That is R squared. And this last one, R squared adjusted, that is a trap. That does mean something. It's just it's not something we use in AP statistics. So R squared is going to be this. Also, because B is greater than 0, that means R is also going to be greater, R is also going to be greater than 0. So when you take a square root of R squared, make sure you choose the positive root. The rest of this stuff, right now, we don't actually need. None of that stuff is really necessary. It will be necessary in a later chapter, just not this chapter. So part A, what is the value of the slope of the least squares regression line, and interpret that. And part B, what is the value of the y-intercept, interpret that. So both parts A and B are interpretation things that we're going to copy and paste from our sentence frames. Once we got our sentence frames copied and pasted in here, we're going to go ahead and get the values. So for part A, what is the value of the slope? Slope is B, and that is 0.729. 0.729. And then how about the y-intercept? Well, that's A, and that's 89.09. Okay. So those are our values. The next thing we're going to do is we're going to substitute all the things that we're supposed to know. First of all, we'll substitute the values for slope and y-intercept. Next, I'm going to note that the value of slope is positive, so I'm going to change this to be increasing. And next, I see a unit here, and units are in millimeters, so I'm going to change that to millimeter. Next, we're going to put things in context. So our explanatory variable, what is the explanatory variable? That is going to be the length of the squawfish. Next is the response variable. Our response variable is the maximum salmonid consumed. Okay, everything is looking really great. Let's read this and adjust for readability. So for every increase of 1 millimeter in the length of the squawfish, that sounds good. The maximum salmonid consumed increases by about 0.729 millimeters. That reads really well, actually. So I'm not going to worry about adjusting that for readability. Or I have adjusted it, and we don't need to adjust it. Part B. The value of the maximum salmonid consumed. Okay, the value of, that's probably redundant again. So the maximum salmonid consumed when the length of the squawfish is 0 is 89.09. Okay, I'm not super happy with that, but I think that's close enough. Let's read through that one more time. The maximum salmonid consumed when the length of a squawfish is 0 is 89.09. Okay, notice that really doesn't make sense. There is no squawfish with a length of 0. Okay, and I also noticed that I messed up the units on that one. Cool. Back to my other point. The y-intercept doesn't always make sense. It only, the y-intercept only makes sense if your explanatory variable has data close to 0. If there's no data close to 0, then it doesn't make any sense at all. Why would you? If you're looking at salmonids who are typically about, I wouldn't even know what it would be here. It's like 90 to 120 millimeters long. Why would you be predicting all the way at 0 millimeters? It's just kind of too far away. It's extrapolating in the negative direction, really. What's the maximum salmonid you would predict for a squawfish whose length is 375 millimeters? We've done this a few times already. Start off first with the LSRL equation. Okay, we have the predicted maximum salmonid consumed, and that is, again, our context for the response variable, is 89.09. I think I showed you where to get that number for the value of the y-intercept, plus 0.729, which is the slope, multiplied by the length of the fish, millimeters. Next, substitute the value for how long that fish is. Okay, we have a fish that is 375 millimeters long. And lastly, do some mathematics. Okay, so that gives us a predicted maximum salmonid consumed is 362.5 millimeters. So letter D, we have it looks like the residual question. We've got a 414 millimeter squawfish consuming a 219 millimeter salmonid. So find the value of the residual for this squawfish. So our equation is RAP. We know that the squawfish actually consumed a salmonid that's 219 millimeters in length. So we'll place that with 219. And now we just have to find the predicted. And just like before, the predicted is just the mathematics of the least squares regression line. We'll do that real quick. Okay, so using the same technique that we did in letter C, we predicted that this salmonid is going to, or this squawfish is going to consume a salmonid that at maximum is 390 millimeters. Well, now that we can have that, we can put our prediction into our residual equation. Great. That tells us that our residual is negative 171.9 millimeters. Okay, and if you just take a look at the mathematics just above it, that means we predicted that we predicted 390 and the actual was 219. So our prediction was much greater than the actual salmonid eaten by that squawfish. So that's it for this one, everyone. That last free response question took a little bit of a toll. We've got one more question to do, number 13, and we'll see you for that video next. Ciao.